Hey there! Today I'm going to present my project called Understanding the CMB Temperature Spectrum. So, we know that the cosmological principle says that our universe is homogeneous and isotropic on large scale. So, we need a metric that satisfies this principle. This metric is equation 1. Also, this metric has to satisfy the Einstein field equations. So, that's how we got the Friedman equations, equations 2 and equation 3. These equations describe the dynamics of our universe. Equation 2 can be written as equation 4 in function of density parameter. We have density parameter of matter content and we have density parameter of curvature. For matter content we have baryons that in cosmology different from particle physics means ordinary matter. Then we have cold dark matter, cold because dark matter cannot be relativistic particles. Then we have radiation that are photons, neutrinos, and gravitons if they exist. Then we have the contribution of curvature. The goal of this project is to find these values, the values of the cosmological parameters. To know that, we need to go to the early universe. In the early universe, we know that photons and electrons have interacted by Compton scattering. This interaction induces a perturbation in the temperature. This interaction can be described by Boltzmann equation as equation 9. So, replacing the Bose-Einstein distribution here in the left side of the equation and the collisional term for Compton scattering, we got the Boltzmann equation for photons, that it is the equation of evolution of the perturbation in photons temperature. So, we can solve this equation, equation 10, with a software called CLASS, that means Cosmic Linear Anisotropic Solving System. To solve this equation, we need to set the cosmological parameters. So, in order to fit the data from Planck collaboration 2018, I set the cosmological parameters. So I found that the density parameter of curvature is around zeros. That means the universe is flat on large scales. Then we have that ordinary matter is only 5% of the universe. Then we have that radiation has very contribution in the universe. Then we have cold dark matter that is around 26%. And then, as we saw in equation 4, the sum of density parameter of matter content and curvature has to be 1. But we don't get that if we add all these terms. So where is the rest? This rest is related to dark energy. So this is the density parameter of dark energy that is modeled as a cosmological constant, and this is just the 70% of the universe. So I was playing with the cosmological parameters, and I looked for a universe with no dark matter. So I set this density parameter to 0, and I plot this line, this yellow line. Yellow line is for no cold dark matter, and blue line is with cold dark matter, that it is Landau-Syrien model. So as you can see, yellow line is completely out of the data from Planck collaboration 2018. So that means that we cannot live in a universe with no dark matter. We need dark matter in our universe. Then I was playing with that density parameter of curvature. So I set the density parameter of curvature to minus 0.3, and I found that the green line that describes a closed universe is completely out of the data, as you can see. So it's not possible to live in a closed universe. Then I set the density parameter of curvature to 0.3 for looking for a universe, for an open universe. So yellow line, as you can see, is completely out of the data, and again we cannot live in an open universe. So finally, conclusions: observations from the cosmic microwave background set and constrain cosmological parameters. Then we need dark matter and the energy in our model, in our theoretical model. We don't know exactly what dark matter it is. We don't know if dark matter is a new particle, and we need to go beyond a standard model of particle physics to explain that, or we don't understand gravity in large scales, and we need to go beyond Einstein's general relativity. If we know a little bit of dark matter, we even know less about their energy. We only know that their energy is related to the expansion of the universe, and it can be modeled as a cosmological constant or modify gravity too. Then, as we already saw in the last figures, universe cannot be open, universe cannot be closed, universe has to be flat on large scales. Thank you so much.